Shaurya? Shaurya?
Yeah, yes, sir.
So could you get?
Yes, sir. I'm
So could
walking
you?
through that error term thing. Just one
Huh,
part I didn't get, but rest of all I got.
why didn't you get the error part? Tell me. I mean, where
The
actually?
in this last one only, the error, you multiply two things and then one of them they're disjoint, so it goes to zero. So the
See,
uh,
logically, yeah, I got your point. Logically, what you are getting? Logically, basically, you are getting that these two segments are disjoint, right?
yeah,
So they are independent. Graphically, I'm talking about graphically. If you see the graph, if you see the line,
yeah,
they are disjoint, so they are independent. Now, mathematically, what you are getting? Summation of this whole square. This is A and this is B. So A plus B whole square. So it is A square plus B square plus 2AB. Now, what will be the 2AB? Tell me, what will be the 2AB?
multiplication of the cross terms.
Summation of
The y hat minus y bar and then uy bar.
U hat.
Ha hat.
U hat I, right? Now, if I just go for simplification of it, then I can write it as summation of y hat I into u hat I,
Ha, that we have proved to be zero.
right? And what is the other component? Minus y bar into summation of u hat I.
Yeah, this I didn't get.
See this one, if you multiply it and then take the summation, then I can rewrite this 2ab. I'm basically talking about the 2ab component. So it will be summation of y hat I into u hat I minus y bar, because y bar is a constant term, so it will come out of the summation. So I will have y bar minus y bar into summation of u hat I, and summation of u hat I is 0, that already we have seen.
Yeah, yeah, got it now.
So now both the components will be cancelled
Yeah,
out.
yeah, got it.
Okay. So that can be proved mathematically, and also you can argue from this diagram.
Yeah, understood now. Thank you, sir.
So this is very important derivation actually. This is very important derivation. Why I am saying so? This derivation actually gives us the R square value. It also gives us, subsequently you will see, other test statistics. So this decomposition of total deviation into the explained part and the unexplained part is very, very important. And regression analysis, when we go for selecting the most appropriate model, often we emphasize on picking up that model where this explained part is very high, or I will say where this residual part is very low. In the sense that higher this explained part, that means this estimated model is capturing larger part of the variations in Y. Say for example, I am estimating a consumption function with respect to income, and I am getting R square value only 0.2. That means income can explain only 20% of variations in consumption. And a large part of variations in consumption remains uncaptured. It is possible that there are many other factors like family size, number of household members in the family. That may be an important factor. Sorry. Similarly, there may be many other factors which might be influenced. Say, for example, in that sample households, if I have observations from rural areas and urban areas, there is a possibility that the consumption expenditure will vary depending on whether you reside in urban areas or in rural areas, because consumption expenditure may also depend on your proximity to the market, availability of information, etc. So if one has proximity to the market, then maybe consumption expenditure would be higher, even if that person has the same level of income as somebody else is having. So the consumption expenditure may differ depending on many other factors, along with income, of course. Now, if I find that R square value in a model is only 0.2, that means the model has very low ESS, explained part. Explained sum of square is very low vis-a-vis the total sum of square. So one possibility is that I have missed out some important variables. It is also possible that consumption depends on income following a quadratic relationship, not exactly linear relationship the way I have assumed. I think you have studied in consumption theory that when you started with a linear consumption function and subsequently you have studied that as income increases, consumption increases but at a decreasing rate. Means marginal propensity to consume declines with increase in income, and the consumption function becomes quadratic. Maybe this R square value will change the moment I bring in the quadratic component, because when I'm assuming the linear relationship, the quadratic part remains uncaptured, and that may result in low ESS and high RSS. So this is a very important derivation, and in subsequent discussions you will see the importance of R square in regression analysis. But at the same time, as I said earlier, we will also be discussing that neither it is necessary for a model to have very high value of R square, nor it is necessary that if a model has low R square value, we will discard it. At the same time, we will also discuss the fact that a very high value of R square with hardly any individual coefficient statistically significant, it may be a matter of concern because it may signal presence of the problem of multicollinearity. We'll discuss on these aspects in detail later. So tell me whether up to this part it is okay. Is it okay?
Yes, sir.
So now what I'll do, I'll just go for some other components. So what we discussed there, to some extent they are written here. So this already we have discussed. Y bar is equal to y hat bar. Already we have discussed on this, that summation of u hat I, y hat I, that is equal to 0. And just now we discussed that TSS is equal to ESS plus RSS. And this derivation, what I was telling Surya, it is written here. Basically, I am talking about this part. So it is a square plus b square plus 2ab. So when I am going for decomposing this 2ab component, I am getting 2 into summation of y hat I into u hat I minus 2 into y hat bar. Again, here I have used y hat bar, but you know, already we have proved that y hat bar is nothing but y bar. So this into summation of u hat I, and again this will be cancelled out. And then I am saying total sum of square is equal to explained sum of square plus residual sum of square. So we have completed our discussion up to this point. But this derivation has a very important relation with reference to our discussions on inclusion of intercept into the model. Now you see, if I don't have intercept in the model, then summation of u hat I is not necessarily equal to 0. If this is not equal to 0, then y bar is not equal to y hat bar. If y bar is not equal to y hat bar, I cannot write it like this. That I know simply this. What I am doing here, I am simply subtracting y bar from this side and y hat bar from this side. And I am doing this only because I have this. So if I don't have summation of u hat I is equal to 0, I cannot write y bar is equal to y hat bar. I cannot write this. Second, if u hat I is not equal to 0, means if I don't have intercept, then I cannot have this, because summation of u hat I, y hat I is equal to 0, that is also based on the property that summation of u hat I is equal to 0. So if I don't have intercept, I don't have this summation of u hat I is equal to 0. If I don't have this, I don't have this, I don't have this, and then I don't have this. And if I don't have this, then whatever R square will be getting in the process, that may give misleading conclusions. Is it okay? Hello?
Yes, sir. Understood.
Now,
You
there may
scroll up
be a possible question for your exam. I may ask, based on this discussion, that explain what will happen if a model doesn't have intercept. what type of statistical issues may arise if the intercept is dropped from the regression model. Then you need to explain all these things. And this is what we were discussing in yesterday's class. It is not simply a question of adding or dropping intercept from the model. There may be some statistical consequences, as we discussed. Second, I also discussed this in today's class. Remember, while doing the Excel, the work in the Excel, I was writing this, that ESS is equal to beta hat square into summation of small xi square. This is explained sum of square. And as I said, yi is equal to alpha hat plus beta hat xi. Then y hat bar is equal to alpha hat plus beta hat x bar. You just put these two here. You will get beta hat square is equal to summation of xi square. I also told that if I square the correlation coefficient between x and y in a bivariate model, I will get capital R square. How am I getting? You know, this is the formula for correlation coefficient. Cob of xy divided by standard deviation of x and standard deviation of y. Now R square means this whole square. So through simplification, you will be getting basically an expression like this. And you know, this is nothing but ESS. This is TSS. So essentially it gives me R square. Again, there is another very interesting derivation here. That is expressing the slope coefficient, that is beta hat, in terms of correlation coefficient. Somebody was asking me that why are we getting into the correlation coefficient? You see, I can rewrite this regression coefficient in terms of the correlation coefficient. So beta hat can be written as equal to the correlation coefficient into sigma y by sigma x. How? Again, the derivation process is given here. What I am doing? Beta hat is, this is the formula we know. And I am just rewriting this formula in this way. What I am doing? I am decomposing this summation of xi square in the denominator into two. One is square root of summation of xi square, and again square root of summation of xi square. And then I am multiplying here in the denominator. I'm adding square root of summation of y hat I square, and same thing I am adding in the numerator also. So summation of xi square is decomposed into the square root terms, and this part is added in both numerator and multiplied in both numerator and denominator. Then what I am getting, if I divide both the numerator and denominator by 1 by n, if I divide by n, then what I am getting? This as the correlation coefficient between x and y. And here I am getting it like this. And this is nothing but sigma y, and this is nothing but sigma x. So this regression coefficient in a bivariate model can be expressed as a function of the correlation coefficient. And you can see very well, sigma y, we know that that is positive, sigma x is also positive. So if correlation coefficient is negative, regression coefficient will also be negative. If correlation coefficient is positive, regression coefficient will also be positive. So what I'll do, I'll upload these two files in team and just cover what we have discussed. Okay. Just cover what we have discussed so far. I think let me just stop here and